So we discuss about potential step. Okay, so we already discussed about this a bit in the earlier lecture, so let me make it clear. So you have a particular potential. So when I say you have a particular potential, it doesn't mean there is a wall here. It just means that there is some potential. And I also gave some examples before in the lecture what this diagram means. So don't think that there is some kind of wall here and particles are coming and hitting the wall. Don't do your classical imagination. Okay, it's not like that. It's just a this is just a representation of some realistic situations we already discussed in our previous lecture. Okay. Okay, anyways, so there is a potential barrier of finite value v naught. Okay, now there are many particles which are coming towards this, but interestingly the energies of this particle, we are assuming that initially they are greater than v naught. So if there, so consider what I want to say here is mm, okay, so consider there is a sheet, transparent sheet. Okay, and say there is a hole here, and this transparent sheet is positively charged. Then electric field goes in this direction. Okay, and there will be a particular potential created. Now if I have another particle with plus charge with energy which is much greater than v naught, then of course classically he would pass through this hole. Let me draw it better. So this is my particle, and my particle will go and pass through the hole because the energy is greater than v naught. You will not get a single case when the particle will come near to the hole and reflect back. This is very weird. Okay, because you know that energy is greater than v naught, so it will pass through the hole, it will not return back. But this is not true in quantum mechanics. In quantum mechanics there are probabilities that it can return back. Okay, when I say quantum mechanics, we are dealing with very small particles and with the wavelengths like of the order of de Broglie wavelength. So you should know in which regime you are going to use quantum mechanics. Not like that you apply quantum mechanics wherever possible. No, you have to look at the regime with the particles and the experimental setup where the quantum mechanics is possible. Here we are assuming that quantum mechanics is possible. Okay, so we are doing quantum mechanical analysis. Okay, so these particles with energy E greater than V naught, they hit this potential. Classically, what should happen? Classically, all these particles should overcome the potential and they should be on the other side. All these particles should be other side. There should not be any single particle which is reflecting back. Classically, this is not possible since energy is greater than V naught. But quantum mechanics says that there are chances that there will be some particles which will be reflecting back. So let us see mathematically how quantum mechanics says this about these things. Okay. Now in most of the book you will see something interesting and a question will pop up in your head. So most of the book what they will do is, so consider you have particles, okay, with momentum or wave vector k1. See, k1 contains the information of momentum of the particle because momentum of a particle is h cross k. Okay, but anyways we are representing the particle in terms of plane waves. So incoming particle is given by plane wave a e to the power I k1 x. Everything looks good. Then I said these incoming particle, some of them will pass through. So let me draw one particle here that pass through. Let me draw some particle 2 or 3. So all these particles are represented by a e to the power I k1x, and all the particles that pass through the barrier, okay, are represented by c e to the power I k2x. But now quantum mechanics says an interesting thing. He says there will be some particles with wave function as b e to the power minus I k1x. So when you have minus I k1x, what does it mean? It means that it is going back in the negative x-axis. Okay, but you will ask a question, this is stupidity. You said that quantum mechanics is going to tell me about this, but why on earth are you assuming from the very beginning that there will be a such kind of wave? This is absurd. You are already assuming there will be such kind of wave. Where is quantum mechanics telling us this? No, 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 no. Quantum mechanics is actually telling us this. Let me tell you how. The way to use quantum mechanics here is as follows. 1. Quantum mechanics says you should make Schrodinger equation. You should prepare the Schrodinger equation and solve it for particular region. So consider this is region with x less than 0, and this is region with x greater than 0. All of you know how to write Schrodinger equation in terms of k and all. Let me show you. So if you have, say, the particles have definite energy, so I write E psi equals. Now this is Schrodinger equation for region x less than 0, because for region x less than 0 there is no potential. So my only Schrodinger equation is E psi is equals to minus h cross square divided by 2m into d square psi by dx. You see, we are dealing with one dimension. Okay, so we are talking about one dimensional systems. So this can be written in a more better way. So it can be written as d square psi divided by d x square plus k1 square psi is equals to 0. So let me write psi 1, okay, to represent that it is in region 1. So I can also say x less than 0 is region 1 and x greater than 0 is region 2. Now what is k1? You can easily see that k1 is nothing but, for x less than 0, it is root over of 2m e divided by h cross. This is the actual k1. Okay, this is the Schrodinger equation for region 1. Now what is the general solution of this Schrodinger equation? Now since this is a mathematical equation and quantum mechanics is more of mathematics, so you should appreciate the mathematics, you should believe the mathematics, you should trust in it. So what is the general solution? This is how the B comes, because the general solution of psi 1 says that a e to the power I k1x is a solution, but the nature of this differential equation that we get from Schrodinger equation is such that mathematically b e to the power minus I k1x is also a solution. So the moment you do quantum mechanical analysis of this scattering, the mathematics itself gives you this part from the equation. This is how the reflected part comes into quantum mechanics. I said we are not assuming it from the very beginning. The quantum mechanical equation is telling us that in the general solution there will be a term with b e to the power minus I k1x, and since it solves the Schrodinger equation, so it is a solution. So this is, we dealt with region x less than 0. Now how about the region x greater than 0? Let's see. For x greater than 0, you can easily write the Schrodinger equation, which will turn out to be del square psi divided by del x square. So for region 2, let me write it psi 2 plus, here let me write it as k2 square psi 2 equals 0. Now what is k2? If you look carefully, then in the second Schrodinger equation you cannot remove the potential because it has potential V naught. So K2 will be 2 2m E minus V naught, okay, divided by H cross square. So here also there will be square. Okay, this is my Schrodinger equation. Now what is the solution of this Schrodinger equation? This Schrodinger equation says that psi2 will have two solutions. One solution will be C e to the power I k2x, just like the a e to the power I k1x. So this is a wave going along the positive x-axis, but there will be one more solution, general solution, which will be d e to the power minus I k2x. But if you look at this problem, then there is not any wave reflected at x greater than 0 towards left. I mean, if you look at x greater than 0, there is nothing which will cause some particle to go from region x greater than 0 to region x less than 0, because the potential exists only at x is equal to 0. So nothing is going to happen at x greater than 0. There is nothing at x greater than 0 which can push any particle towards the left hand side. So this one has to be ignored. It is pure logic. Think about it. Do you see any barrier uh, uh, apart from at x equals to 0? No, there is no barrier apart from x equal to 0. So at x equals to 0, there is nothing that will push the particle towards left. But exactly at x equals to 0, you have a barrier. So quantum mechanically, it can push some of the incoming particles towards the left. Okay. So you got psi1 and you got psi2. Now how the game goes forward? Remember that Schrodinger equation. Let me make a quick comment here. Okay. The quick comment here is the actual psi should be written as what? Actual psi should be a function of space and time. And since we are considering states with definite energy, it can be written in terms of space part and time part. We have discussed this again and again in our lecture. So the actual solution is, say I'm writing the actual solution psi1. Then the actual solution will be a e to the power I k1x, and the time part, which is e to the power minus I omega t. Because you see, the particles has to be represented by a wave-like function. This is just the space part of the wave-like function. Okay, the wave-like function actually looks like this. It should have a space part and it should have a time part. That's why we call a psi as wave function. Okay, so the actual way to write is k1x minus omega t, a e to the power I k1x minus omega t. Similarly, what is the actual way to write psi2? Because psi2 is to be a function of x and t. Okay, in psi1 we have also b. So let's write it here. In psi1 we missed b. So let me write it. So b, it will be e to the power minus I k1x, and the time part e to the power minus I omega t. So what will be the b part? So the reflected part will be b e to the power minus I k1x plus omega t. Okay, this is the actual way of writing the wave function, because when we say wave function, it means it's a wave. It should contain a space and a time part. So how should I write psi2? Actually, it should contain both space and time part. So I can write it like this. The space part will be psi2x and the time part is e to the power minus I omega t. So this one I wrote it directly in psi1, but I'm writing here step by step for psi2. What is psi2x? Psi2x c e to the power I k2 x, and this is e to the power minus I omega t. So what is the actual way to write psi2? It is c e to the power I k2 x minus omega t. Anyways, for a moment you can also forget this thing. Okay, if you don't want, you can forget these things, and let's come back to our discussion. So Schrodinger equation gives us psi1 and Schrodinger equation is given as psi2. What else we can do with psi1 and psi2? There is one more game to play. The game is you have to find the reflection coefficient and the transmission coefficient. So reflection coefficient, so R, is defined as modulus of J incident divided by J reflected, sorry, J reflected divided by J incident. This is reflection coefficient. And then there will be transmission coefficient, which will be J transmitted divided by J incident. Now you would ask, what is this J? Remember, in our last lecture I said whenever there is some kind of flow, it means indirectly we are talking about current. Okay, whenever there is some kind of flow, we are talking about currents. So if I know psi1, then from this psi1, which is I can calculate two things. One, I can calculate J incident. J incident, to calculate J incident, I will use the first part. Remember in our last discussion how J was related to psi? I'm not going to repeat it, okay? And to calculate J reflected, I'm going to use this second. And to calculate J transmitted, I'm going to use this third, C e to the power I k2 x. So how to calculate J1, Jr and Jt? Let me tell you an example. So what is J1? J1 can be calculated by what was the formula? IH cross divided by 2m, and I think there was psi star del psi by del x minus psi del psi star by del. Just please check out with our earlier lecture. Okay, what you have to do here, you will put the first part of psi1 to calculate J incident, just first part of psi1. Okay, and interestingly you will find the value of J incident as H cross k1 divided by m into amplitude A square. How A square? You see, what is psi1? Psi1 is A, but there is a complex conjugate, so it will be A e to the power, let me write it here. So it will be A e to the power minus I k1 x. And what is d psi by dx? D psi by dx will spit out minus I k1, and again I will have A, it will spit out plus I k1, because psi is e to the power I k1x, and psi1 star or conjugate is e to the power minus I k1x. So it will be e to the power I k1x. So you see, in the first I just solved the first one. In the first one, this and this gets cancelled, and there are two a's multiplied. So there is a square from the first term, and there will be a square from the second term. Okay, and they will get added because of some particular reason. There will be addition, and in the end you will get this answer. Okay, H cross k by m a square. Similarly, you can calculate J reflected. Use the same formula, and this time in the J reflected you have to use what? in place of psi you have to use b e to the power minus I k2 x. This is what you have to use, and you can find jr, and jr will turn out to be minus h cross k divided by m into modulus of b square. Here when I wrote a square, it is modulus of a square. Similarly, you can calculate J transmitted, which is equal to h cross k2. Oh, here I should have 1 divided by m into modulus of c square. Okay, now you can easily calculate the reflection and transmission coefficient by using J incident, J reflected, and J transmitted. Okay, here it is, you can see on your screen. So the reflection coefficient is b square by a square, and the transmission coefficient is k2 c square divided by k1 a square. Okay, now the question is all about finding the values of a, b, and c. Now how to find a, b, and c? That's the main question. So let me do a quick review so that you don't get don't miss something. Okay, so we had some particles coming towards a potential barrier, or you can say potential step. Then what happens? Quantum mechanics says some particles will get transmitted, some will get reflected. So we frame the Schrodinger equation for region x less than 0 and for region x greater than 0. And then we calculated the respective psi1, psi2. Psi1 first part contains the incident wave, psi1 second part contains the reflected wave, psi2 first part contains the transmitted wave. Since we know the wave, we can easily calculate the J's, Ji, Jr, Jt. Now since we know the J, by definition of reflection and transmission coefficient, where did I define? Here. You can see this is the definition of reflected and transmission coefficient. From this definition, use these values of J and you will reach here. But the story do not end here. Why the story do not end here? Because we still don't know what A, B, C is. So now the main idea is to find what these coefficient A, B, C are. Okay, so I have written it down. What do you see? To find A, B, C, you have to actually use these boundary conditions. Now how to understand these boundary conditions? Now to get an intuitive idea of this boundary condition, I would again tell you to go to our electrodynamics lecture series, and there we have discussed the reflection and transmission coefficient of electromagnetic waves as well as normal waves. Okay, once you look at that lecture, this particular idea of boundary condition, why the boundary condition looks like this, will be 100% clear. I don't have to teach you this again. Okay, I have already explained how this is the actual boundary condition when a wave is going from one media to another medium. Anyways, so we are going to use this boundary condition. So when we use this boundary condition, you have to specify everything. For example, here you have psi1 0, here you have psi2 0. So what is psi1 0? Psi1 0 means in psi1 put x equals to 0. What was psi1? Remember, psi1 was a e to the power something to into x. It will become 0 because x is 0, so it remains only a. Similarly, the second part was b e to the power minus I k1 x, but x is 0, so only we have b here. So what do I get? I get a plus b. Similarly for psi2, I get only c, because in psi2 what was there? In psi2 we have c e to the power I k2x, but x is 0, so we have only c. So the first boundary condition gives a relation between a and b this way. Similarly, in the second boundary condition, take the differentiation and then put x 0. You get this. Solving them, you get b and c. Now once you get b and c in terms of a, you can easily write reflection and transmission coefficient, which look like this. Because you see, in the reflection coefficient there is a mod a square in the denominator. So once you find b in terms of a, then mod b square will contain a square. So a square in the numerator and a square in the denominator here will get cancelled, and you will be left with a pure reflection coefficient only in terms of k1 and k2. This part, exactly this part, is 100% same as what we discussed in electrodynamics. So go to that lecture series. Only then you can have a clear idea of reflection and transmission coefficient. So in electrodynamics we talked about the classical ideas, and here we are talking about the quantum ideas. And so in the quantum ideas you see that the transmission coefficient is not zero. Of course the transmission coefficient is not zero, because some particles will go because they have energy larger than the potential step. But reflection coefficient, see, this is non-zero. This is the most interesting result, that says that some particles are going to reflect even if their energy is more than the potential. Quite weird, but this is what quantum mechanics tells us.